In this video, I wish to cover a very special method called Euler Substitution. So what does this method even do? So whenever you see integrals in the form of, say, integral of fx dx, and this integrand consists of a square root of a quadratic. You've definitely seen this in your school, right? Haven't you? This is something you use inside the quadratic formula, right? So whenever you see this square root of a quadratic, this method called Euler substitution aims to convert the square root of a quadratic into something linear in a new variable, allowing the integral to become rational. A rational integral is so much easier to handle. In the previous videos, we have also covered another method called binomial differentials, which also converts integrals in the form of xm plus a x plus b to the power of n dx, where m and n are fractions and so hard to even evaluate fractional powers of x, so we convert them into integer powers of t. So similarly in here, our goal is to convert this integral into something linear. So obviously when it comes to a quadratic, there's always three cases. One case is when it is irreducible. Okay, so irreducible. And one case, it has one repeated root. Okay, so that looks something like, say, x plus 2 squared. This is a repeated root. The root is -2, which is repeated multiple times. And two roots, could say rational. That looks like x plus 2, x minus 1, something like that, right? That is a special, this is where the function can be expressed as two roots. So obviously when it comes to your mind, one repeated root is the easiest to solve, because when you're able to express this as, say, d minus z, and when it's a square, this square and the square root cancel out, so it just becomes integral of d minus z dx, which is so much easier to handle. But when it comes to two roots, when it comes to irreducible, there's something like x squared plus 1 equal to 0. How are we supposed to solve for x squared equal to negative 1? It's unsolvable, right? Something like that, or it's something you just cannot factorize. That's when we are going to use this irreducible quadratic. Okay, so in this video I will show you case 1, which is irreducible quadratic. So now let me pull out the theorem. So when there is say, integrand that consists of ax squared plus bx plus c, and the conditions are a has to be more than 0, obviously, and secondly, we require the discriminant of this quadratic to be negative. This is the reason why it doesn't have any real solutions, or it just cannot be factorized, right? Thus, we shall use this substitution. Ax squared plus bx plus c is equal to t minus square root of a times x. Okay, so what does this do? When you substitute this, you're able to convert the square root into something linear. So the best way for you to understand is by trying an example. So we're going to page 88, example 1 of the art of integration. So let's start with trying to solve this integral. So what do we see? Are we able to factorize this? Let's try. B squared minus 4ac. In this case, that is equal to What is b? Well, that's 4 squared minus 4. In this case, a is 1. C. This is 16 minus 20, right? Which is negative 5. Thus, you can conclude that it is below 0, right? Thus, you can conclude that b squared minus 4ac is lower than 0. This is case 1, right? This is the first condition. What's the second condition? A must be below, A must be above 0, right? Which is correct. A is 1, right? A is 1, right? In this integral. So yes, we can apply this special case 1 of the irreducible quadratic. We're going to take the substitution t minus square root a times x. Let's try it out. Substitute x squared, what is it, x squared plus 4x plus 5 is equal to t square root of a. A is 1, so it's just t minus x. Oh, that's simple. So what are we going to do? Differentiate it. So let's do it slowly. Okay, this is x squared plus 4x plus x plus 5 equals to t squared minus 2tx plus x squared, right? So let's simplify. Factor out. Make it in terms of x. Why are we doing this? To differentiate it. When we make it in terms of x, then we are able to differentiate it. So we can, dx is equal to t squared plus 4t plus 5 over 2t plus 2 squared dt. Thus, we can use the substitution square root of x squared plus 4x plus 5 is equal to t minus k, right? T minus x, which is the same thing as t minus t squared minus 5 over 2t plus 2, right? Because we can substitute in here, right? This is the same thing as t squared plus 4t plus 5 over 2t plus 2, right? Now you can evaluate the integral so much easier. So the integral is 1 over square root of x squared plus 4x plus 5 dx, which is the same thing as t squared plus 4t plus 5 over 2t plus 2 squared, which is what we're going to substitute as dx, right? And let's change the quadratic. We're going to change this into the denominator, right? So let's evaluate. It is again t squared plus 4t plus 5 over 2t plus 2, right? dt. Oh my god, this is a handful, right? But what do you notice? It's nice, it nicely cancels out. Right? It just becomes 1 over t plus 2. Isn't this so much easier to solve? And this is a standard integral, ln t plus 2 plus c. Right? And if you back substitute, you get ln of x plus 2 plus square root of x squared plus 4x plus 5 plus c. While we're substituting t is equal to square root of x squared plus 4x plus 5 plus x. So in the end, we get this very sweet answer. Thank you.